And then the first question in the second lecture is, can you really achieve a perfect stoichiometry of the material? I think this one never been an issue for many years. I think recently this is a very, very important issue in complex oxide field. And then because a lot of fundamental science we are working on this complex oxide is really didn't actually go that kind of deeper level, and even didn't know how to achieve the perfect. And we thought it's perfect, but actually realized it's not perfect stoichiometry. So this part of today's lecture, the second lecture, is related to perfect stoichiometry of this system, and then this stoichiometry of stoichiometry is actually offers other functionality, and then you have two sides of the things. Either you need off stoichiometry or you need a good perfect stoichiometry. You have both ways advantages. So I'm going to give today second one, like a lecture I did yesterday. I'm using specific example of the science. Then starting from there, answer these questions later. So this one is work is related to the answer yesterday that one of the professors asked me about the ferroelectricity of strontium titanate. And then this one is emergence of room temperature ferroelectricity and reduced dimension in strontium titanate. The origin of this stoichiometry of the new phenomena, emergent phenomena, is coming from very slight off stoichiometry creating point defects, which is point defects is the origin of this new phenomena. And that this is a good thing, but also the bad thing, certain types of electronic application, for example, mobility or low temperature mobility of this strontium titanate, superconductivity, other types of material properties, and then this defect can be an issue. But I want to introduce something good first, then I want to go to talk about how to get rid of this and some other purpose. So this is actually in 2015, and we have published that. But I think the background of this is actually related to stoichiometry of this material. So initially, I think strontium titanate is not ferroelectric at all. And the certain groups actually reported strontium titanate is ferroelectric. And then people didn't believe initially, okay, how come strontium titanate is ferroelectric? And then this is the work done by the Korean group here. And then this is the, we call reciprocal space mapping. It's showing is the strain and the lattice parameter of the material thin films grown on the substrate. I'll talk about that later because I haven't talked about this X-ray diffraction yet. And this reciprocal space is H and L. This is HKL, which is X, Y, Z in the real space, and the HKL. And then you have this definition of this substrate, strontium titanate. The substrate is a 001 reflection. And then you have a strontium titanate. These are thin films. On top of this is spread a little bit. And then electrode, the strontium leucine bottom electrode, everything lined up here in the H direction, which means everything fully coherent. Okay? Which coherent means substrate lattice parameter big, and then your film is that, and substrate that. There's all different layers they can use. A layer with the in-plane lattice parameter, but it's actually everything coherent, all lined up, perfect stoichiometry, perfect coherent growth. And then, so when you look at this one, from the tetragonality, they see that strontium titanate is ferroelectric, but from this measurement, your tetragonality, your expansion is a lot higher than bulk material. But the origin of this one is not coming from intrinsic. It's coming from a lot of defects. It's sputtering of the PLD, is a bombardment, and it's not real strontium titanate. It's off-stoichiometry or very bad off-stoichiometric film. I think that's one is strontium titanate ferroelectric. And then, so this large off-stoichiometry can creating this one, but this barium titanate single crystal compared to do this, and then this large tetrangulating, you can actually see that, and you can see you deposit low pressure oxygen and more than like a high pressure oxygen, and low pressure one is more defects because you have an oxygen vacancy creating volume get bigger, because this is the main reason, and then creating this ferroelectricity is a lot of oxygen vacancies. Okay. So that's what they reported this one. But also we have found that so many years ago, I mean, we have the work on strontium titanate, we believe, and this strontium titanate is the geometric film, and we posited pulse laser deposition. And then this measurement, a direct constant measurement, and then PR measurement, you see that low temperature, you start to see some kind of like strain films, and then you have this kind of ferroelectric polarization, and even strain-free film is a no strain at all, strontium titanate on strontium titanate, and you have the remnant polarization. However, when you measure the PFM measurement as a function of time, and then you have some kind of decay of this polarization is actually strain-free film, and the strain film, and they really fastly decay, but initially you can have certain type of polarization inside the material. Okay, so this is something background of something is going on in strontium titanate. At that time we actually conclude that strontium titanate has a nanopolar regions, which means your ferroelectric like polar regions is patched in between the matrix of dielectrics. So it's not everything is ferroelectric. It's a small patch of those things, and then embedded in the dielectrics. So that means it's not long range is connected to each other. So if macroscopically you measure it, you don't see it. But certain measurement shows indication of ferroelectric like behavior at room temperature. Okay, you understand this one? So is uniformly the material you're supposed to be complete dielectric, strontium titanate dielectric room temperature. But you have a very small patch, is like a ferroelectric like material that we call nanopolar region. So that's NPR or PNR, polar nano region. Some people use PNR. Polar nano regions embedded in the matrix of dielectrics. But this one is all isolated and that doesn't do anything. Okay? But specific, like this measurement shows some indication of it. So what we have to do, originally we studied this one is not the point defect studies we studied. We actually studied this nanoscale, the ferroelectricity and strontium titanate. And one of the important question people is asking is when you go reduce the dimension, your ferroelectric material lose ferroelectricity at low dimension. Okay, because there's a lot of theory papers talking about this one. Like a size effect, this is a theory paper, is a nature paper, and then so when you grow barium titanate, this barium titanate is ferroelectric in the at room temperature. But when you reduce the dimension, smaller and smaller, like this one is m equal 10 unit cell, and 8 unit cell, 6 unit cell is smaller and smaller, and you have this kind of energy, low energy here, and then you get the ferroelectricity. But some point you don't have like a plateau at the bottom, and you lose the ferroelectricity. So there's a reduced dimension, and you lose the ferroelectricity, and then this is the work initially mechanism to understand overcome size effect. That's one of the reasons we have to study. And then, but starting point here is coming from many years ago. We thought about some nanopolar regions embedded in here. Then, can it be ferroelectric if that is embedded in the matrix region? So think about very simple question. you have all solid, even in the most perfect crystalline contain defects in resulting in local disorder. And that is we call nanopolar regions, like a small dot local inhomogeneity capable of creating polar nanoregion, PNR, in dielectrics. This is actually like a ferroelectric regions, but it's actually matrix of dielectric. So when you apply electric field, you don't feel anything. You cannot really switch this one. Do you understand this one? Okay. Then, one thing you can think of here, well, can you make this one ferroelectric? Okay, so PNR is initially we realized that PNR, polar nanoregions, when you grow film at the time, we measure the Raman measurement. Raman mode actually shows something polar mode of certain mode of the Raman measurement. So you look at these two, and then this is the films have a different types of film, bulk single crystal STO, and then here nearly stoichiometric STO. But films we have off stoichiometric STO, you have a very strong peak here coming from certain polar peaks, and then we have a single crystal doesn't have one. But thin films have these kind of peaks. Okay, that is coming from polar, and then in the mode of the in the Raman mode. And then, but why it didn't show any ferroelectricity this one? Because it's embedded in between. But Raman measure everywhere. So the ideal first starting point is what is the nanopolar region, what caused these nanopolar regions, and then is in the pure strontium titanate. So we did some literature search, and some literature shows that there's a stable defects in strontium titanate, the titanium anti-site defect in strontium vacancy site. For example, you have an almost perfect stoichiometry, but you have a very, very slight off stoichiometry, strontium deficient. Okay, the strontium deficient, then you have two possible defects. One is strontium vacancy. For example, you have 99%. Okay, you have a 1 and 0.99. One is titanium, 0.99 strontium. You have an extra titanium. So you have an extra titanium, you have two ways you can actually compensate this. One way, strontium is vacant because you have a less amount of strontium. Or you have a strontium site, is titanium goes to strontium site. This is called anti-site disorder. Okay, you know, point defects going to A site, your B site atom goes to A site, that's what we call anti-site one. And that's a known defects calculation previously, and we did a calculation that is really polar or not. So we asked the DFT calculation and calculated we have a strontium in this anti-site titanium and strontium site. What is the actual size of the polarization of this? So we worked collaborate with the DFT person and measure 3x3 supercell calculation and measure what is the actual polarization. And this polarization shows quite high polarization, around the 60 microcoulomb per square centimeter at the center of this region. The reason of this polar nature of this, think about this. You remember that I showed back in titanate, the titanium atom ions is shifted in the middle, right? The up and down with respect to the oxygen. Remember that the first lecture I showed you? And the strontium site, strontium -2, +2 is a lot bigger than titanium +4. So the ionic size is a lot smaller than actually size of the vacancy. So that when you go, the titanium goes in, and this one is not in the middle, it's shifted. Okay? So energetically more stable, is shifted from the center, is like 0.8 angstrom is off from the center, which is polar. Okay? So the calculation, and then this energy calculation is large polarization, and also your polar direction is either 1, 0, 0 is more stable. So the direction of this shift is along the 1, 0, 0 direction, not the 1, 1, 1 or 1, not polar axis step. So this is a large off-center of anti-titanium atom, and then this one reasonable barrier for the switching here. So there's a switching from here, switching here, going back and forth, and the natural formation of PMR, strontium titan, intrinsic point defects, which means not perfect stoichiometry, but they're creating anti-site that makes polar nanoregions. Then, how do you make this one ferroelectric? Okay, so this nanopolar regions is actually in the matrix like this, because this one is no particular screening of this, and that's complete random. Okay, orientation of polar regions, complete random. So, to make this one is a bulk like this. So that's why when you measure this, is a paraelectric, and then size of PNR is very, very tiny, nanometer scale. So simple thing is, from the intuition, can you reduce this to very thin? Then these nanopolar regions touching the bottom electrode, touching the surface. Okay, if that happens, and you have an observate on the surface, and bottom electrode make this region looks like ferroelectric. Okay, this very simple thinking is, when you have a nanopolar region, the length scale of the thickness, length scale of the nanopolar region, we don't know what the size of nanopolar regions, but when you approach to get thinner and thinner and thinner, you approach the size of nanopolar region, you will be able to see the ferroelectricity. That's a very hypothesis in the beginning. Okay, so can you test this? It's stabilizing polarization of PNR or interfacial compensation, because your polarization can be screened by metallic free electrons, and then the bottom electrode, top electrode, and the bottom electrode and then your top electrode has different screening power, and then that's why you have this, but you can switch over this one. So we actually talked to this one to phase field simulation, not previously with the DFT calculation, 3 by 3 by 3 superset calculation to measure the polarization, to determine the polarization. But here phase field simulation actually measure, it can be stable when you reduce the thickness, and then this polarization value, macroscopic polarization value, how it happens. Okay? So this is the retention, relation steps, and then your simulation step, your time scale. And then your time scale, you have a thickness is so thick, and this, when you switch the polarization, it just dies so quickly, very similar to what I show a PFM measurement, previously like a time scale measurement, the PRL paper. And then when you get thinner and thinner, at a certain point, and it doesn't die, it will maintain this polarization infinite amount of time. Okay? So you have a crossover here, certain crossover of when you reduce the thickness, when you're touching this one, top and bottom electrode, this one becomes very stable ferroelectric. Okay? So that's our hypothesis. So you don't test this, you look at the polarization as a function of thickness, and thickness get thinner and thinner, and then your polarization go higher and higher, but the higher thickness polarization is so low, and that's not stable. So we grow this one, postulate to that position, using single target, which means using strontium titanate single crystal target. But when you transfer this to the target, you never be able to get exactly same composition. It's maybe 0.1% off. That's still enough to create this kind of point defects embedded in between. And then you make this one bottom electrode strontium luthenate. Because screening of this bottom electrode like here, you need a bottom electrode and the strontium luthenate. So first you deposit strontium luthenate first, then you grow the strontium titanate, different thickness of strontium titanate, either 12 in cell or 16 in cell, varying the thickness of film, and trying to measure when you really see the crossover. Okay, So you grow this, you count number of this oscillation, then that's a number in itself. And here is really important, you have a precise control of number in itself. So when you measure this, and the strontium luthanate, strontium titanium, you measure this, it's from the X-ray diffraction point of view, it looks like a pure strontium titanate. You cannot really distinguish substrate and thin film. That means your off-stoichiometry is very, very small. But still, it's not perfect stoichiometry. They're creating point defects. I think that's what our hypothesis. And the surface is very smooth, and then you have and a very, very small one. But when you measure this Raman measurement, and you still see this kind of polar peak here. Okay, so up to room temperature, it's 300 Kelvin, you see that this peak. So this peak actually drops as a function of temperature, but still room temperature you have certain peak. And we also took the sample, and this is a chemical MD, I'll explain it later. Okay, this one is supposed to be perfect stoichiometric film. It's very close to 1-to-1, like a bulk single crystal, and it doesn't show polar peak in this kind of one. Okay, this is grown differently. It's not regular MBE. This one we call chemical MBE. I'm going to talk about that later, and it doesn't show this. So this one does not have these polar nanoregions, but this one has a polar nanoregions. Even though it looks like stoichiometric film, but you have a very miniature of a small amount of point defects. So we actually measure this by cross-sectional TEM, and we call STEM. And then this STEM allow you to do this kind of this bright one and dark one, and then you actually see the oxygen, and then this is the B site, or this is the B site, titanium, and titanium, and you have measured actual shift of this titanium, and then you actually see this magnitude of polarization is actually significant, and all pointing down, because screening of strontium luthanate is a lot better than top is the observate of the moisture or whatever things. So this is the indication of polar nanoregions as I show on the schematic diagram. Remember that? So it's, when your thickness approaches smaller, and this kind of polar nanoregions is actually doesn't exist, and then pointing down everything like this. Okay, so you measure the titanium, this off-state of this displacement here. This is can be seen. This all the size of arrow and direction is displacement of displacement with respect to oxygen. Okay, so this direct evidence of polar nanoregions. What's the size, what direction of it, and then looks like the thin films, ultra thin films, has some kind of screening of it. So can you really measure ferroelectricity of this? So you measure, this one is this 120 unit cell thick film. It's a thick film. So that means your polar nanoregions embedded, but it's not really screened by a power of metal electrode. And then when you write this one, positive and negative, and then this one immediately disappears. It doesn't maintain it. Remember that I show you thick films here decays so fast. Remember that decays? The time scale, you measure it, it's already gone. You don't see that. Okay? So when you have a change the thickness of the film, then certain point you will be able to see that stable polarization by PFM. But 120 unit cell is here, and that dies right away. Okay, that's what the data showing here, this data. When you have something 60 unit cell, and they have a certain maintain that time scale, but it's going away, that time scale. But 12 unit cell, you see that? Very stable. Okay? You write the domain and then maintain forever. So that means our hypothesis is these nanopolar regions reduce the dimension, and you can make a ferroelectric material at room temperature. Okay, so that's one way you can measure. by PFM. But we also can measure this one by other method. But this one is interesting. We have, like most of materials, your ferroelectricity reduced the dimension and then disappeared. That's what I show you first slide, the theory calculations and other measurement. But in here, ferroelectricity, the non-ferroelectric material actually become ferroelectric at reduced dimension. That is breaking the conventional wisdom. Is when you go smaller, something disappear. But here, non-ferroelectric become ferroelectric only in reduced dimension. Okay? So we also measure by a P rule. The P rules of a 24 unit cell, you clearly have remnant polarization. 120 unit cell C1 looks dielectric. And then your pond measurement is also shows thin one, very clear ferroelectric, and then 120 unit cell and nothing. Okay? So that is evidence of this ferroelectric emergence of ferroelectricity in non-ferroelectric strontium titanium material only reduced dimension, and that is coming from all these nanopolar regions. And then you can actually use strontium titanate as a lot of interesting tunneling resistance measurement, but potentially, and then this one can be used ferroelectric combining with the lanthanum aluminate strontium titanate 2D-dimensional gas. I haven't covered this one yet. I'm going to talk about it tomorrow. And then you can combine the ferroelectric and then the 2D-dimensional gas and strontium titanate. You can create new functionality, and then including 2D conductivity and dielectric functions, and even superconducting magnetism in the 2D electron gas. And that offers a lot of other possibilities. And then you can attune it by polarization non-volatile way. So you have strontium titanate can be non-volatile ferroelectric, and that contains 2D electron gas and superconductivity and magnetism. So that's something very exciting. And then, but this one is initially defect. Everybody want to get rid of defects, but you can use this defect can create new functionality. So that means you have your sometimes when you're looking for certain research, your direction, then you got some negative things, but it turns out to be very useful for some other reasons. Okay, so this one also has a quite good retention with time, and 12 unit cell retention is really good as a ferroelectric barium titanate. And but very thick film 120 unit cell dies so quickly, and then that's something is 2 hours later, and then it's just after writing, and then this 2 hours later 12 unit cell it maintain is quite well. Okay, so now implication is inverse enhancement of ferroelectricity. Dimension is get reduced and ferroelectricity actually coming. So this is a new insight in nanomaterial science. And you get smaller, you can create new, and then simple and general rule, new design rule for ferroelectric and ultra thin films. And then this one is not limited to strontium titanate. Any dielectric material creating nanopolar regions, you can do the same thing. And I use the strontium titanate as an example, but this one lanthanum aluminate, calcium titanate, other one can be ferroelectric at reduced dimension. So that offers it's a nano electronics, oxide nanoelectronics, and then the possibility and beyond this. So next one, I'm going to come back here. Initial question I ask you: how to achieve perfect stoichiometry? We already have a lot of defects and an interesting ferroelectricity, but now these defects can be detrimental to certain types of properties. So in most complex oxides, I said that state control is one of the most challenging issues, and reduce their point defect concentration. And as I said, MBE techniques, as I showed initially, conventional flux control, even read or the QCM, quartz crystal monitor, and at least 0.1 to 1%, and this defect concentration roughly 10 to 20 per cubic centimeter. It's a lot. Okay, so that's the level of your defect concentration. Considering semiconductors, what is the doping concentration of your wafer? Silicon wafer coming as received 10 to the 15 per cubic centimeter for dopant. Okay, that's the base of the doping concentration and p-type and type wafers. When you make some device doping 10 to the 18 and 10 to the 20, that's a region, that's making active regions. And this is a lot, 10 to 20. You need to make it better to make a really electronic device which is sensitive to the defects. So something, point defects, is always exist in any material system. And emergence exotic phenomena, as I show you, room temperature, ferroelectricity, nanopolar regions. That's what we talked about first part. But point defects can be multiple origin here, stoichiometric control, and then energetic deposition, like a lot of energetic particles is hitting here, and then or some impurities. Okay, but I'm going to address this stoichiometric control to avoid anti-site disorder, which is anti-defect is the main defect. Okay, so this reducing the defect, and then very important for quantum transport, especially when you quantum transport measurement, you need the extremely high mobility of the material, and then in order to do that, you have to reduce it, the quantum Hall effect, and then those things. Initially, like a fractional quantum Hall effect in gallium arsenide, and they have very high mobility gallium arsenide, and then that's the reason they were able to do that. They shared the Nobel Prize. Horst Stomer and Dan Sui, and then Bob Lasting, and they have those initial. And the reason they were to do that, gallium arsenide is the defect concentration so low and very high quality of materials. So I think one example here, what we learned during our process. When you grow this two-dimensional electron gas, lanthanum aluminate and strontium titanate, bulk single crystal, and you get very nice two-dimensional electron gas behavior. But when you grow PLD grown strontium titanate and then grow NaO, this is a homoepitaxial strontium titanate. You see, we expect the same material. Because yesterday I told you it's homoepitaxy and heteroepitaxy. Do you remember that? So homoepitaxy means I grow same material on top of the same substrate. But strontium titanate grow strontium titanate, and we expect this one is same as this. But when you do NaO on top and supposed to have here 2d electron gas, but some reason this one is insulating. That means this strontium titanate and this strontium titanate are not the same. Why is not the same? And then when you measure X-ray and everything, looks the same. But very small amount of impurities or defects, and maybe the origin of it. And then that's a very important reason we have to work hard to get this stoichiometric film. So actually growing this stoichiometric film is putting this rock on top of this cusp. And try to go there and roll back this way, and hard to put on top here. Okay, so try to grow control of flux. You put in a little bit of B, then go here and roll back here. You try to go a little more A, roll back here, and never reach that the top here. It's extremely difficult in terms of flux control rules of two flux. And then when you do growth by single target, you have even same problem too. Okay, so the way PLD grown thin films by controlling this actually change of laser energy density. Okay, that's one of the parameters you can control this flux and then this stoichiometry. And depending on laser influence like low energy to high energy, 0.1 to a few joule per square centimeter, and you see that this lattice parameter is reached at stoichiometry like castle, like this. That means very hard to get one point here, even though you make a measurement here, range of this. So that means almost impossible to do that perfect stoichiometry, this method. So you have to do something totally different way of thinking. And then this is the technique shown, MB and then PLD sputtering, same kind of cusp shape. What is the approach to avoid this cusp and then make a wide range of these and then solve the problem? And then you need this kind of mountain. You can make this kind of mountain. You can stoichiometric window is broad like this. Then you win. How can you do that? So, in order to do that, what is actually make this kind of processing window? And then this window can be done by thermodynamic determine the stoichiometry, and let thermodynamics can let figure it out. Not you figure it out. Thermodynamics, because it's actually thermodynamics is very important, and then solve this problem. What exactly mean is this known technique is a gallium arsenide process. You know the gallium arsenide growth? Anybody know gallium arsenide growth process? There's a gallium and arsenic growth. Is we call absorption controlled growth. At very high temperature, the arsenic is very volatile. Arsenic is vapor pressure is very high. Your sublimation temperature is very low. So that means you're trying to deposit arsenic on arsenic surface. It doesn't stick. Okay, it does not stick on the top of the arsenic, but as long as you have a gallium on the surface and arsenic attached. So that means you have a gallium surface, one monolayer gallium, then you deposit one monolayer arsenic, even though you provide a lot more arsenic and doesn't grow anymore until you have a gallium attached to the surface. Okay, this is what we call absorption control process. It's known in gallium arsenide. Okay, so can you do same thing in oxide? Can you do oxide system similar to this kind of absorption control growth process? It's already known that works. If you have a very, very volatile species, and you can do that, which is something somebody asked question during the break, it's like a PGT growth. Lead is volatile. Okay? Lead is volatile, and at very high temperature, lead doesn't stick, lead just go away. But lead also providing a lot of flux of lead. If you have other element, the zirconium and titanium on the surface, it sticks, but not more than one layer. It just dissolved. Then until next titanium or zirconium arrive. This is what we call absorption control. So this lead oxide, this is window, the lead titanate growth, depending on what kind of solid in the surface, and you have a different regions of phase diagram. The stoichiometric growth window is quite broad here, and this is what we call absorption control. Okay, so it's very important you understand thermodynamics and then the growth. This is temperature and then gas process, gas pressure. This is gas pressure of the torr. So when you when you increase the lead flux, lead oxide flux, when you go higher and higher and higher, and they go higher, you have a window here. You have this in this region, the lead oxide doesn't deposit. Lead oxide can be just a volatile. And but this region, lead oxide is actually go away gas and only form the lead titanate. And this region, you have extra lead oxide deposit. Okay. So you have a narrow window, but still your plateau can grow no matter how much flux you provide lead oxide, still you get only lead oxide, lead titanate. Do you understand that? You understand? So this region, you provide the extra lead oxide, but that's only gas phase go away. And then does not form extra lead oxide formation. So this is what we call absorption control, and due to high volatility of lead oxide. But strontium titanate does not have volatile species. Titanium and lead is not volatile. You cannot do that. So strontium titanate case, you have strontium and then you have this kind of phase diagram, and titanium is this kind of phase diagram, and then you have growth window for strontium titanate maybe somewhere here. If you have certain species can do like a absorption control, but can you do this way? So what we did here is this is a too high temperature. Temperature is a 1400 degrees C. Okay, can you do this one? It can be done similar way, but the temperature is too high. Really, you cannot achieve that way. And then this region, pressure is too low. You look at this one, strontium pressure, and this temperature, and this window, the reasonable growth window, what you do, your heater, what temperature heater you use. Your heater temperature, only 800 degrees C. Can you go your heater temperature up to 1400 degrees C? And you can do laser heating, but normally it's hard to do that. So reasonable strontium oxide pressure 10 to minus 9 torr, your background pressure 10 to minus 9 is MBE level. But reasonable temperature 800 degrees C, to do that, your vacuum level has to be better than 10 to minus 20 torr. 10 to minus 24 torr vacuum chamber, I don't think you can grow. You can make those vacuum chambers. Surface science growth chamber maybe 10 to minus 12. But 10 to minus 24, in order to get this kind of pressure of the strontium flux, your base pressure has to be even lower than this. 10 to minus 30, 10 to minus 40 torr, which is impossible to achieve. So that means you cannot do that using strontium oxide, relying on strontium oxide volatile species. Then you have to do something totally different approach. What is the approach then? Then you have to find volatile species is not elemental source, something different. This is organic source. And then this organic source has, they call, this one is actually developed by the Santa Barbara group, the Susan Stemmer's group, and then they have used, they call TTIP, titanium isopropoxide, and then they call TTIP, and then you have a structure looks like this, but titanium is attached to oxygen and another organic around here. But this one is a liquid phase at room temperature, but when you heat it up around 100 degrees Celsius, then it becomes gas phase. The gas come out, and the gas actually is when you attach to here on the surface, and that is very volatile on the surface. Okay, so use this one, TTIP, high vapor pressure, contains oxygen atom, and this one can be desorption limited feature around 700 degrees Celsius, which means it's a growth temperature rather than this kind of like a very unreasonable temperature, 1400 degrees Celsius, and then you can achieve desorption control limited growth around a little bit higher than 700 degrees. So this hybrid MBE, the deposition of strontium by strontium source, the metal source. For flux of TTIP is an organic source. Okay, this TTIP is this one, and then this one has like absorption control like gallium arsenide and lead oxide, very low temperature. Then this is the first report of absorption control growth of strontium titanate, and what they show here clearly, you have a strontium rich region and titanium region. You have plateau. Can you see the plateau here? And this is a lattice parameter measurement as a function of your TTIP flux. So which means you provide TTIP flux, titanium actual source, increase the higher and higher and higher, and then from 35 to 55, and you have in this region the strontium rich, but this region titanium rich because you get a lot of titanium, but you have no change in between those two. And those regions clear plateau, and then when you go low temperature, this plateau is narrower. Okay, so that means this plateau can be wider and wider and wider because you're easily to do absorption control. But you can get 800 degrees C quite useful window to do that. You can do 900 degrees C, 1000 degrees C even wider, but this is more than enough to achieve striking material wide window. And then more surprisingly important here, they actually measure the electron mobility at low temperature. And this film, lanthanum doped strontium titanate, your mobility of this over 30,000 at low temperature. This value is even higher than bauxite crystal. You dope it, lanthanum in bauxite crystal, mobility is lower than thin films grown by this technique, which means your defect concentration or off-stoichiometry of this one is almost perfect. And more importantly, you have a wide region of plateau. As I showed initially, you have the caustic tube flat, so you can actually roll your rock on top of this, and that's exactly what this one shows. And then, so now, I think we know how to actually get this technique. And then you can use this chemical MB, and then providing its chemical source as titanium. But it's not limited to strontium titanate. And then other groups are working on, and this one, strontium vanadate, or like a vanadium, has a different types of precursor, and then they demonstrated exactly same kind of absorption control and perfect stoichiometry strontium vanadate. And then also like the stanate tin, the strontium got barium stanate, barium tin oxide. It's also its high mobility material, and also that can be demonstrated in absorption control. There's a lot of possibility as long as you know certain precursor of the element can be work in a range of certain temperature, and then absorption can be controlled in that region. So I'm going to stop it here, and then I think that I started from questioning, can you really achieve perfect stoichiometry? The answer here is yes, you can achieve it using this technique. And then that allow you to achieve extremely high mobility of this. And then otherwise, and then this material can be very high defect concentration, may be very useful for other type functionality, as I demonstrated, ferroelectricity and reduced dimension. So I want to stop it here, and then I will take some questions about this. The second one. Yes.
Can we create artificial PNR regions?
Artificial PNR regions.
Artificially we can create in some other system to achieve ferroelectricity at reduced dimension.
As I show here is some of the dielectrics calcium titanate. We expect the calcium titanate can be behave the same way. So as long as you have the titanium is we have calculated like titanium is creating anti-site in the strontium site. For something like for example, if you have some ion damage or something, may create similar polar energy. But I think that's artificial. You can add some defects there. But additional defects is we have to coming from other source of outside, maybe ion damage of the material. Maybe that's a possibility. Any other questions? So then tomorrow we'll start. Okay, so that's today we learned the thin film growth. We have two different lectures about sputtering, and then second one is extreme control of stoichiometry, and then how this point defect plays a role. And tomorrow I will talk about atomic layer control growth. But it's atomic layer control that really actually makes big difference in the interfaces. So when you make some interfaces, you have to really precise control what the termination, what it is. So tomorrow we'll talk about not only technique, it's one example of 2D electron gas, and I will talk about it. Okay. Some more questions? Is it clear? Okay, so we learned something here about the growth, and then if you have any questions about general other growth technique, I can bring that. But I think those two are our main message here. I think. Okay, then you can stop the because somebody is coming.